for Sustainable Development, organized by the Department of Mechanical Engineering, Prestige Institute of Management and Research, Bhopal, and sponsored by ATAL Academy.
बस
It is an honor to introduce Dr. Rahul Agrawal, an accomplished academician and researcher specialized in solar thermal technologies, thermal energy storage, and advanced material for energy applications. With a PhD in mechanical engineering from the National Institute of Technology, NIT Jamshedpur, Dr. Agrawal has made significant contribution to the field of renewable energy. Dr. Agrawal has an impressive research portfolio. Dr. Agrawal has published extensively in high impact international journals with 24 publications, including 7 papers in SCI Index journals, 5 in Scopus Index journals, and 12 papers presented in international conferences, showcasing his expertise in areas such as phase change materials, nano enhanced thermal systems, and battery thermal management. He holds 6 patents and authored 1 book and contributed 5 book chapters. His research on integrating advanced materials into energy storage systems has been widely recognized for its innovative approach and practical applications. In addition to his research, Dr. Agrawal has been instrumental in mentoring students, guiding innovative projects, and contributing to professional development initiatives. He has receiving several accolades, including patents in solar energy systems and awards from his contribution to engineering education. Join Dr. Rahul Agrawal in this session to explore the latest advancement and trends in energy storage technologies, which insights into their role in renewable energy integration, grid stability, and sustainable development. Uh, Please, Rahul sir.
Yeah, I'm audible.
Yes, sir, you are.
Yeah, thank you so much, Rohit sir. And I'm very much thankful towards the management of Prestige Institute of Management and Research Bhopal and ATAL Academy to provide me a platform to share my knowledge, what I had gained. So good evening to all. I'm Dr. Rahul Agrawal, and today the topic of presentation in today's FDP is the energy storage technologies. What actually is the energy storage technologies and why it requires? What is the need? Actually, we need it or not? That we can realize from the theme of this FDP. The theme basically it's the innovations and challenges in adopting clean energy technologies for sustainable development. So as the name come sustainable development, so we are thinking about the clean energy technologies. Either it can be renewable sources of energy, it can be solar or the wind. And as we are thinking towards this sustainable, clean energy technologies, so we are getting for the innovations, what the development we had done in the renewable energy systems. So actually, a lot of research has already been carried out and still going on to enhance the effectiveness, efficiency, and performance of the renewable energy systems. And apparently, the main focus is to enhance the productivity or the capacity of the renewable energy system, either it can or the wind. But the major challenges what we are facing actually is the storage of that amount of energy. As we are totally focusing on the production of the energy, but actually in reality, if we'll talk, the development we are doing, the 30% of the total solar and wind energy we can store according to recent scenario. So in today's presentation, we'll discuss about what are the hurdles, what are the challenges, and store, how we can store what are the technologies that are used to store the uh, solar energy. So, is my screen is visible or is screen is changing? Slide is changing.
Yes, sir. Yes.
So, this is the outline of my presentation. We'll discuss about the energy storage technologies. What actually is the energy storage technology? What is the need of energy storage technology? And what are the different types of energy storage technologies? And basically, we'll deal, there are so many types of energy storage technologies available that we are using in a broad sense. One of them is the thermal energy storage, and we are discussing broadly for the thermal energy storage, and it also includes about the sensible heat energy storage systems and the latent heat energy storage system. So what actually is the energy storage technology? Basically, energy storage technology or the systems is a device that is used to store the excess amount of energy that is producing during the peak hour and can be used uh, that is used to capture the excess amount of energy, and that amount of energy can be used at a later time or during the off-peak period. For example, if we'll talk about the energy that is present about the renewable energy systems, the major drawback with the renewable energy systems is they are intermittent in nature. For example, if we'll talk about the solar or the wind, so they are mostly dependent upon the time-wise daytime or the wind speed basically. So major problem, and we'll talk about the solar PV. Am I audible?
Yes, sir. Yes, sir.
Okay. Now, if we'll talk about the solar PV, which is the cheapest source of electricity, but without storage, it cannot be properly harnessed. The only way to put more of that PV into grid or into national plans for capacity expansion is the need of the energy storage to match demand and production of electricity. The same we will talk about the non-relevant sources of energy, which include the fossil fuels, which includes the coal, petrol, and the natural gases that does not require a lot of storage because we can use whenever we require. But the same is not with the renewable energy system, which is known as the clean energy technology that we are more focusing nowadays. If you will talk about the evolution of renewable energy, and nowadays basically the evolution of renewable energy is taking place in the two distinct phases. The first phase is from 2010 to 2020, in which the overall pricing, if we compare the overall pricing of the energy, what we are getting from the renewable energy is quite same as compared to the energy we are getting from the fossil fuels. This is because of the certain incentive plans we are getting from the government or the subsidies on the installment of the renewable energy systems. But at the same time, the new projects, the huge increase in the new projects has become, has placed a huge pressure on the national grid system, which typically can absorb around 30% of the new solar and wind power that is generated. So these are the basic problems that we are facing with the renewable energy systems. So actually, it is a need that we have to store the solar, basically renewable energy. So basically, these energy store technologies are essential for balancing energy supply and demand, ensuring reliability, and enhancing the efficiency of energy systems. And the energy storage provide a solution to achieve flexibility in demand and supply, enhance the grid reliability, because we'll discuss later about the what actually required for the grid on grid systems. It requires a continuous supply of energy. It enhances the grid reliability and power quality and accommodate the scale up of the renewable energy. So this is all about the energy storage technology. Next, why actually is the need of energy storage technologies? What is the need and what the steps our government has taken? At the previously, we'll talk about the when the solar mission has launched. We are not talking about the storage. We are generally discussing about how we can increase the production of the renewable energy sources. But around 8 to 9 years, a lots of missions has been arised that really works for the energy storage system. Now, basically, at COP, that is Conference of Parties, that is held in Paris in 2015, India made a commitment to derive 33 to 35% of its energy from the non-fossil fuels or from the renewable sources of energy by 2030. And actually, the target set was that we have to achieve 175 gigawatt of renewable energy by 2020. So the tremendously increase in the generation capacity, that is from 175 gigawatt by 2020 to 500 gigawatt by 2030. So in this 8 years of span, we have to work a lot to increase the capacity of the renewable energy sources and to achieve this, it must require new policies and
तो मैं लेके आ रही ये क्या तरीका है बेटा टीवी ऑन करना है अच्छा 2 मिनट रुको पहले हम लोग अंदर चले आ रहे 2 मिनट रुको जा रहे हैं
sorry. So basically, the sudden increment in the goal to produce the energy from 175 gigawatt to 500 gigawatt force the government to form the new policies and the program. And as we discussed, according to the current scenario, we are only able to store the 30% of the energy. As what we can do about that energy? So for that purpose, to achieve the targets, the integration of the distributed generation resources is done with the low voltage grid systems, including the rooftop solars. It requires the supports from the active demand response and energy storage system that are essential to maintain the grid stability. So basically, to achieve that target, the more emphasis is given on the low voltage grid and the high voltage grid for their flexibility and their stability. Now, to obtain this objective, of this increased capacity of this power generation, an National Energy Storage Mission was launched in February 2018. It was launched by the Ministry of New and Renewable Energy, which includes the representative from the government ministries, industry, and research institutions and experts to plan the strategies how to produce the electricity and how to manage the storage of the electricity. So for that, National Energy Storage Mission was launched. Now, in the March 2019, the initiatives were later moved to Niti Aayog, and they had again launched the new storage mission with the transformative mobility and energy storage mission. And later on, to support the energy storage mission, that of the government of India, India Smart Grid Forum, ISGF, in collaboration with the India Energy Storage Alliance, IESA, had joined, and their main focus is to the grid integration up to 40 gigawatt of the solar rooftop installation. So we can understand that as we're talking about the energy storage technologies, so from 2015 to 20, and that we can see the energy roadmap for 2019 to 2032, this approximately 13-year the roadmap has been decided to see the problems of the energy storage, okay, how we can work out. So there are a lot of work has been carried out by the government of India and already being done, and lots more have to be carried out. Now, here are certain points and what actually we need the energy research technologies. The first is the integration of the renewable energy. But as we know that we are shifting towards the renewable energy technologies, we are shifting towards the renewable energy technologies. So, and we also know that the renewable energy sources like solar and wind are intermittent by nature, as they depend on weather conditions and time of day. For example, solar panels generate electricity only during the day, while wind turbines depends on wind availability. So the energy storage systems can store excess energy generated during the peak production time and release it during periods of low generations, ensuring a stable and reliable energy supply. The next point is the grid stability and the resilience. So what actually the modern power grids, because the major problem, the electricity what we are producing from the solar PV panel, the excess amount of energy we are transferring to the on-grid systems. And the major problem with the grid is that they require a continuous supply of energy. Means they will not work on the fluctuating energy. The fluctuating energy we are supplying. So the grid stability and resilience is a major problem. So the modern power grids face challenges such as fluctuating demands, aging infrastructure, and increased penetration of distributed energy resources. So the integration of the energy technologies help by balancing supply and demand in real time and acting as a buffer to mitigate power surges, outages, and other disruptions. The next is the decarbonization goals. So basically, if you're talking about the energy, triple E's, energy, efficiency, and the environment. So whatever we are doing to enhance the performance, effectiveness of any system, so we have to keep in mind the environment, that it must not affect the environment. So decarbonization. So basically, countries worldwide are setting ambitious goals, gas emissions. Okay. Electrification of mobility. So basically the rise of electrical vehicles, as we all know, has significantly increased the need for advanced energy storage solutions. Now, energy access and rural electrifications. So basically, if we talk about the rural electrifications, in rural areas, the off-grid renewable energy systems reduces dependency on the diesel generators. The reliable power supplies for critical services such as healthcare, education, and communication will help by the application of the energy storage technologies. Here are some of the economic benefits like minimizing energy wastage or lowering electricity prices by utilizing the energy during the peak period by storing that amount that we are wasting it. And there are so many applications that we'll discuss later on also. Next, we'll move towards the types of energy storage systems. So there are a lot of energy storage systems are available, and a lot of research is already going on to enhance the power capacity to store the amount of energy. First is the mechanical energy storage system, electrochemical energy storage system, chemical energy storage system, thermal energy system, and the electrical energy. These all different types of energy storage system basically represent a different specific type of energy, in which energy they are storing the energy and then they are transferring it in the electrical power. For example, we'll talk about the mechanical. So there are three types of mechanical energy system we are using. One is pumped hydro storage system, compressed air storage system, and the flywheel. This all the systems. First, they are storing the energy in the form of mechanical. Then they are transferring that mechanical energy by some or other means or some of other devices into the electrical energy. Similarly, in the electrochemicals, we are using the batteries to store the energy in the chemical form, and later on we are getting the directly electricity. Chemical, we are using hydrogen as a source of energy. Now, if we talk about the electrical, we are using superconductors we are using to store the amount of energy, and then later on we are converting it. Now, the major sector is the thermal one. Thermal, there are again 3 or 4 types of basically storage systems are there. It can store the energy in the form of sensible heat, latent heat, thermochemical conversions also we are using, and the cryogenic conversions that we'll discuss later on. All these things. So these all are the energy storage system. Basically depends upon the type in which the initially form they are storing the energy. Next, we're discussing about the mechanical energy storage system. This is the pumped hydropower or hydroelectric energy storage system. So as we see, it is the mechanical type of energy storage system. This is the most important and most used energy storage system that is widely used all across the world. Basically, it includes the 2 reservoirs, artificially created reservoirs, or we are finding the sites or the locations where we can create these reservoirs. And both the reservoirs are at different elevations, one at higher elevations, one at the lower elevation. And in both the reservoirs, they will act as a dam to store the water. From the upper reservoir to downward reservoir, we are keeping a powerhouse in between. Powerhouse, which includes the generator and the motor. What actually is the working? When the water is stored at a higher level, means during the peak time, when we require the energy, during the peak hours, when we require the energy, the water stored in the upper reservoir is supplied through this penstock, and as the water comes through this penstock, here the nozzle, we are placing the nozzle is placed here, and the nozzle converts the potential energy into the kinetic energy. So here, the potential energy is being converted into the kinetic energy, and as the water strikes the turbine, the turbine rotates, and the generator shaft is coupled with the turbine.
नागपूरला अहमदाबादकडे थंडी नाही पडत.
And the turbine shaft and the generator shaft is coupled with the turbine, which further moves toward the electrification process. So as the turbine rotates, it produces the electricity, and the remaining power in the remaining water, after delivering its potential energy into kinetic energy is converted into the mechanical energy, and mechanical energy is further converted into the electrical energy. This power is again stored in the lower reservoir. When the excess of energy is required, when the system produces excess of energy and we didn't require it during the off period, this power is again pumped with the help of the excess energy. This water in the lower reservoir is again pumped toward the higher reservoir with this excess energy. So this is the actual working of the pumped hydroelectric storage, and it has a huge capacity to transfer the power. It has certain advantages that it can high power density. It is a low operating cost. And so many examples are there, benefits are there. And here are some of the pumped hydropower projects that already in working conditions in India. And we'll talk globally. The world largest water storage plant is in USA, Bath country, USA, 2,710 megawatt. And we'll talk about the India. The first hydropower plant, basically, is launched in 1970. It is in the Nagarjuna Sagar in Telangana district of 705 megawatt. Here are some of the list of the plants, hydropower plants, energy system that already been installed and being in functional, basically. So the Nagarjuna Sagar that is located in Telangana, and basically it has a capacity of 705 that we already discussed. Like Kadamparai, it is located in Tamil Nadu. This project has a capacity of 400 megawatt. Now Tehri, it is located in Uttarakhand. This project has a capacity of 1000 megawatt. And Sila Hala, this is located in Tamil Nadu. This project has a capacity of 1000 megawatt. And still, there are so many projects that are still in the working condition and about to be installation. Likewise, and approximately in Gujarat itself, 2,750 megawatt capacity plants are located in several 16 different sites with the maximum power capacity of, I think so, 1450 capacity plant is going to be installed in Gujarat. Now, next, the mechanical energy system is the compressed air energy storage. Now, what actually it is similar? It is similar to the pumped hydro power storage system. In it, basically, in compressed air storage, we are compressing the air with the help of the motor when off peak electricity period or when we are producing the excess amount of energy. So what we are compressing the air which are naturally available in free nature, naturally available, we are compressing the air with the help of the compressor, and we are stored beneath the ground, in the underground, in the metallic carbons. This is the metallic structure. Beneath the ground, we are storing the excess amount of energy, excess amount that compressed air. And when it required during the peak hours, we are using that compressed air and we are running the expansion turbines. The compressed air is used to run the expansion turbine, and the expansion turbine to the pressure turbine is again coupled with the generator, and it can produce the electricity. So basically, it is also a source of basically energy storage technology that basically depends upon the mechanical. Next is the flywheel that basically we all know that flywheel stores energy mechanically in the form of kinetic energy. As the load, as the power producing capacity of any systems increases, subsequently, the flywheel stores energy by increasing its kinetic energy, and then it delivers back the stored energy by releasing the speed of flywheel itself. So basically the same principle, flywheels are working that they take an electrical input to accelerate the rotor up to speed by using the built-in motor and return the electrical energy by using this same motor as a generator. But the major drawback with the flywheels are not suitable for long-term energy storage. We cannot use for long-term energy storage, but can be used for the load leveling and the load shifting applications. Flywheels are also known for the long life cycles. Such a life cycle is quite long. High energy density, it can store a huge amount of power, low maintenance cost, and quick response speed. So basically, these are some of the features of the flywheel. And as we seen, these three, either pumped hydro storage system or the compressed air storage system of the flywheel. These all are the mechanical type of storage system in which, in first case, we had stored the potential energy. We had convert the potential energy to mechanical energy. In the second, we had convert the compressed air energy into mechanical energy. And the third flywheel, we had convert the kinetic energy into the mechanical. And later on, all this mechanical energy is further converted into the electrical energy with the help of the generators or the electrification processes. Next, come into the minds electrochemical storage. Now we'll talk about the electrochemical storage. It includes the battery energy storage system. We can say the battery energy storage system. And as we know, if we have to transfer that, we had already discussed the huge amount of, we are planning for a huge amount of capacity of the renewable sources. And we know that the amount of electricity we are producing using the solar PV panels, that we have to transfer to the grid, systems to store that excess amount of energy. But the major problem with the grid is it requires the consistent power. It requires the consistent power because it will not require the power as the solar radiation will fluctuate during the daytime. The power production by the PV panels, it will get the fluctuating power with the PV panels, or in the night time will not get the power. So it is quite tough to store the power what we are producing with the either wind or the solar only itself to store in the grid. So basically, a technology that can be used to firstly store the power that are produced through the grid into the battery. Then we can use that power in the early morning times or the peak periods. We can store the power in the battery, and we can deliver that power into the we can transfer that power into the grid. And the other examples we had already discussed about the electrical vehicles, that the batteries, the main source of the electrical vehicles, the batteries, the dependency on the battery itself. So there are so many types of batteries are available, and batteries, as we know, that batteries are used in the portable electronics, or we are using in the grid-based electricity generation systems. Now, the major requirement nowadays for the batteries is we require the more efficient and larger batteries that can work well with more user devices, ongoing devices, and the storage applications. So batteries is basically classified into two types. Use and throw batteries, that is non-rechargeable batteries. We are calling it the primary batteries. And the rechargeable batteries that are used in our cell phones, laptops, UPS system, we are calling it as the secondary batteries. Now, basically the secondary types of battery or the rechargeable battery that we are using in the renewable energy storage grids and the transportation technologies like EV. So here are so many types of batteries that we'll discuss in the next slide are available, and depending on the several characteristics we are using according to our need. So these are the lead acid batteries. So we'll go for the working of the lead acid batteries. So this lead acid batteries consist of basically it contains electrodes made of two different materials. This is the electrodes. One is the positive and one is the negative. It is made of two different materials. The materials used is one electrode is of metal and second electrode should be of the metal oxide. If we're talking about the lead acid battery, the one electrode is made of lead and the other electrode is made of the lead oxide. In between the electrodes, in between the container, within the container, we are filling the electrolytes, which contains the ions and the electrons in solution. Now, these ions, basically, electrolytes can be liquid, so we are calling it a bed cell, and
ये सारे प्राइवेट कॉलेज वाले जो पढ़े हुए हैं
and it can be basically a solid form. So we are calling it a dry cell. Both electrons and ions can enter or leave the electrolyte solution from the electrolyte surface. So electrical energy in electrochemical systems provided by the oxidation and the reduction process occurring at the opposite electrodes. So basically, this is the different types of battery energy storage systems that we are using. And on the different types of parameters, here is the comparison between the different, like lead acid batteries, nickel cadmium batteries, sodium sulfur battery, lithium ion, and the sodium nickel chloride. These different types of 5 different of batteries that has been comparative analysis has been done on the basis of the specific energy, specific power that is generating, life cycle, how many times we can discharge or charging the particular type of battery, charge and discharge efficiency, and the self-discharge phenomenon. These are the comparative analysis. And here is the comparison of the different energy storage systems. Like as we said that pump hydro, the maximum amount of power that can be stored. Now we can store the maximum amount of power with the help of the pumped hydro, approximately 3000 megawatt. And then compressed air, then modal salt we can use. So these are the comparative analysis for the discharge time, also maximum cycles of lifetime, energy density, or the efficiency. So this is the comparison between the different types of energy storage systems. Now the next what we are going to discuss measure on the thermal energy storage. As previously we had discussed about the solar PV systems, that solar PV or wind energy, basically renewable energy. So we had discussed, or we had taken the name so many times of the solar PV, how we can store the energy that is generated for the PV, solar PV cells. But as we all know that the energy that is harnessed from the sun can be in two types. We can harness the solar energy either using the solar PV or the solar thermal. By the application of the solar PV systems, we can directly convert the solar energy, solar radiations into the electricity with the help of the PV, and that we are using, we are storing and we are using for certain applications. Regarding the solar thermal technologies, we are converting the solar radiations first into the heat, first thermal energy in the heat, and then we are using that thermal energy or heat into a specific required applications. Either it can be for the solar cooker, it can be of the solar water heaters, solar desalination process we can use. We can use in solar space heating, solar dryer, anywhere we can use. So the equally important is the storing capacity of the thermal energy. As equal the important, as we are focusing the storage of the solar PV, the storage of the thermal energy is also very important, as we are highly dependent on the solar thermal applications in our practical life, basically. So thermal energy storage, it includes basically on the basic principles. Like if we'll talk about for any solar thermal applications, we'll talk about the either solar cooker, solar water heater, solar stills. What actually we found that we are getting the maximum amount of solar radiation during the peak hours. Peak hours, it depends upon the geographical locations also, but maximum we are getting the maximum amount of solar radiation between the period of 10 to 3. What the amount of energy we are getting the excess amount of energy that time. Please mute. Okay, so we are getting the excess amount of energy that we required. From that excess amount of energy we required during that peak hours of 3 to 4 hours. So it is necessary, and later on the efficiency or the effectiveness of the system highly declined in the later hours and in the morning hours also. So it is the need to store that amount of energy which is quite high during the peak hours. So the technology we are using to store the excess amount of solar energy that we are getting during the peak hours is basically in the form of the thermal energy storage. And there are so many types of thermal energy storage systems available. Sensible heat storage systems, latent heat storage system, thermochemical heat storage, and the cryogenic heat storage. Basically, these all thermal energy system depends upon the certain specific applications for which we require, like upon the temperature, upon the amount of heat we required. All these things, all of the thermal energy systems depends. First, we discuss about the sensible heat storage material, sensible heat storage systems. Basically, what actually happens? Sensible heat. Sensible heat is the amount of energy that is being stored by any material without changing its phase. For example, if you can see here, now this is a case of the PCM, but we can see here will case of the water. If water here at 25 degrees Celsius, and as we know, at normal temperature pressure, at the normal atmospheric condition, the melting point, the evaporation boiling point of the water, is 100 degrees Celsius. So as we are increasing the temperature of water from 25 degrees Celsius to 100 degrees Celsius, the energy that is stored within the water or within the any material is called the sensible heat. That is, its phase is not changing up to the 100 degrees Celsius. And for changing its phase, it requires the latent heat. When we are providing the latent heat, then the water is changing its phase at constant temperature, that is on 100 degrees Celsius, and stores the latent amount of latent heat, and it gets converted into the vapor. And again, vapor, when we are increasing the temperature of the vapor to either the degree of superheat we can call, or we can call the sensible heat. It again stores the sensible heat. So basically, there are so many materials. So in solar thermal systems, we are incorporating the sensible heat storage materials to store the excess amount of solar radiation that we are getting during the daylight hours, and we are storing that excess amount of energy, that storage amount of energy, in the later hours during the off sunshine periods. Basically, and we are mostly using in the domestic applications like hot water heating, space heating, concentrated solar power plant, and many more we are seeing. So these are some of the examples of what we are using as a sensible heat storage material, like white marble, black stones we can use, pebbles, calcium stones, iron scraps, we can use steel wool fibers. So many things we can use that can store the excess amount of energy. And the sensible heat, what stored, the formula everyone knows that Q is equal to mCp delta, the mass of the system, water, what we are, and delta is the temperature difference. This is the amount of heat what we are going to store. And here are some of the materials that is basically used to store the sensible heat. Here is the practical applications of actually the sensible heat materials is used. Likewise, pebbles is used in the solar steel. Solar steel is an apparatus that is used to convert the brackish or the saline water into the pure water. So this is the solar steel with pebbles as a sensible heat storage material. Here it is a double slope solar cooker basically, and it we can see the container and the pipes. It includes a thermic oil. The thermic oil has the capacity to increase the temperature up to 500 degrees Celsius without decomposition. So thermic oil is used to store the heat as a latent sensible heat within the solar cooker. This is a steel wool fiber. A steel wool fiber has also capacity to store the sensible heat, and basically it has the additional property, weakening property, to increase the surface area of the water. Here in the next one, the marbles are used. Marbles are used as the sensible heat storage material. Next comes the concept of the latent heat storage material. So basically, for any thermal energy storage system, there are two important factors that we have to keep in mind. First is the high energy storage density and the high heat transfer performance. The energy storage density should be high and the heat transfer rate should be high. So this is the major important or key factors for any thermal energy system that we are lagging in case of the sensible heat storage material. So basically, to store a large amount of energy, we are utilizing the latent heat thermal energy storage system. The basic benefit for thermal energy system at that it can store a large amount of heat, amount of energy by a small amount of material. The material what we are using in latent heat storage systems is the phase change material. Is the phase change material. So what actually is the phase change material that will yesterday Dr. Ravi has also discussed, and we'll see what the practical applications of the phase change materials. So phase change materials basically it is a substance with a high heat of fusion, or it contains a high latent heat which melting or solidifying at a certain temperature and is capable of storing and releasing large amount of energy. Means phase change material can store a large amount of energy and it can release that amount of energy while changing its phase, either it's melting or solidifying. Here are some of the working principles of the PCM that, as we had already discussed, basically the application of the PCM, it depends upon the temperature what we required on the solar thermal systems. For example, this is a certain example that we will take the example of the paraffin wax. The paraffin wax has a melting point of approximately 56 to 58 degrees Celsius. In the normal system, we'll keep in the solar cooker. Solar cooker, the normal temperature in the initial period is to 27 to 28 degrees Celsius. As the solar radiation strikes, as the time passes, the temperature of the basin increases, and at the same time, the temperature of the PCM also increases. When the PCM in the initial phase up to the 64 degrees Celsius, up to its melting point, the PCM stores the sensible heat within itself. Means from 23 degrees to 64 degrees Celsius, it stores the sensible heat. And after 64 degrees Celsius, when the heat is continuously striking to the surface, solar regions, the PCM stores the heat energy in the form of latent heat. PCM stores the energy in the form of latent heat, an enormous amount of energy that is already defined how much energy a material can store. That is latent heat, we are calling it. So a huge amount of energy is stored by the PCM during its melting process. As the temperature rises above 64, as it increases to 80 degrees Celsius. So first it is in the solid phase, it changes its phase and it converts into a liquid phase. And now the temperature is again increasing from 64 degrees to 80 degrees Celsius. Now this is the time. As the time passes away and during the off sunshine period, so basically what are the major challenges with the solar thermal application, that we are getting very less efficiency during the off sunshine periods, and during the night hours or later hours, the efficiency of the system is very less. Why? Because we are not getting any source of radiations or source of energy in the later hours. What this PCM plays a critical role, it releases the amount of energy. First, it releases the stored energy that is in the form of the degree of superheat, or we can call sensible heat. It releases that amount of energy within the system's solar. So it again enhances the performance of the system. Then as it reaches, the temperature goes down. As the temperature reaches to 64 degrees Celsius, the PCM start to release the discharging phenomenon, we are calling the charging phenomenon and the discharging. The PCM starts to discharge or release its stored heat within the system. So the actual amount of heat required to perform the system, it's getting with the help of the PCM, the stored energy of the PCM. And subsequently, the PCM releasing its heat during the late hours also, and our system is quite effective in the late hours also. So this is the general, basically, working of the principal fission material. There are classes and there are a variety of PCMs are available in the market. Basically, it's classified on the material properties, chemical properties. It's organic PCM, inorganic PCM, or eutectic PCMs. Organic paraffins we are using commonly. alcohols we are using, poly, polyols, esters we are using for organic PCM. In organic, we are using salt hydrates or the molten salts. In the eutectic PCMs, we'll discuss about that we are mixing two different types of PCM, either organic, inorganic, or of the same type we can mix. Now the PCM is further classified depending upon the application where we are using, upon the melting temperature, low temperature PCM, medium temperature PCM, and the high temperature PCM. If we will talk about the low temperature PCM, so it will work that where the temperature range is below 100 degrees Celsius. Below 100 degrees Celsius, and we'll talk about the practical applications. It is working on the basically space cooling, space heating applications. In the building sector we are using, and the paraffin wax, fatty acids, polyethylene glycol, hydrated salts, these all are the generally comes under the category of the low temperature PCMs. If we will talk about the medium temperature PCM, the PCM that working under the melting temperature range within the 100 degree to 200 degrees Celsius, 200 degrees Celsius. So that comes, and the examples, practical examples we are using, solar heating applications, solar cooker. Here we are using the medium temperature PCM, which includes the salts, hydrated salts, calcium chlorides, and so many. And for the high temperature PCM, when the temperature range is below 200 degrees Celsius, which includes the concentrated solar plant applications, waste heat recovery systems, where the temperature of the system is greater than 200 degrees Celsius, and we require the PCM that works, that melts higher than the 200 degrees Celsius. So for that, the molten salts, like eutectics, also solar salt we are calling it, molten salts like sodium hydroxide, sodium carbonate mixtures, metal alloys, that all we are using for this specific applications. There are certain images of the PCMs, the paraffin wax, stearic acid, sodium chloride is an inorganic PCM, magnesium chloride hexated is an organic PCM. These are types of PCM that we're using. Now, a concept came of binary eutectic PCM, because PCM, that is phase change material, that available in the market, we already know its properties. Like the major property we have to go through while selecting the PCM, that we'll discuss also, but the major two things, like the melting temperature, what is the melting temperature of the PCM, and how much is the latent heat of that PCM. So in practical applications, we see that it's quite tough to select, or it is quite impossible for the every type of PCM to get be proper for a specific applications. So to obtain a specific latent heat or specific melting point, so what we are doing, we are mixing two different types of PCM in a specific ratio. We are mixing two different types of PCM in a specific ratio, so that the required properties what we need for our application part, solar thermal application part, we will get from that PCM. So basically, the development of eutectic PCM by mixing two or more different types of PCM augments the thermophysical properties so that they can be used for specific applications. Now, the advantages, what actually is the advantages? Are the capability to achieve more result like specific operating phase change temperature, that what phase change temperature we require that we can achieve, or high latent heat capacity for each volume. And now the thing came to our mind that how we came to know that if we are taking two different types of PCM, we'll check also in the later slide that we are mixing, we'll do the process, how we are preparing the nano enhanced PCM or the bioelectric PCM. We are preparing two different types of PCM. We are taken two different types of PCM like palmitic acid and the stearic acid. This both PCM has specific properties of melting point and latent heat, both. So how we know that how much percentage of how much specific weight ratio we have to take to get our specific property that what we require. Either we go for the experimental like 10 degree palmitic, 90 degree stearic, 20 degree palmitic, 80 degree stearic, and all the time we have to mix them, and we have to go for the DSC techniques that will we find out the latent heat and piston temperature. So what is the mathematically equation is a Schroeder equations. A Schroeder equation is there. By that equation, we can calculate, right? We can calculate the mix eutectic PCM melting point and the latent, what is the latent heat of fusion, what actually is the value of the latent heat of fusion. With the help of the Schroeder equation, we can find out. Now, this is the basically there are so many drawbacks for the PCM. The major drawbacks is less thermal conductivity, and the second drawbacks, we are not getting the PCM of our specific choice. Either the leakage problems of the PCMs. So for that, to enhance the thermal performance of PCM, we are using certain applications, like we are using nanoparticles, integrating nanoparticles to increase the thermal conductivity. We are using form shaped stable PCM or shape stable PCM, that is basically to eradicate the problems of the leakage problem. We are developing eutectic PCMs. These all are the certain techniques by which we can enhance the performance of the PCM. Now here is the nanomaterial embedded PCM that basically we can, the major drawbacks with the PCM is the low thermal conductivity. And because of the low thermal conductivity of the PCM, the energy storage capacity is get reducing and increase the time required for complete melting and solidification process. The time required for complete melting and solidification, it is quite high, and the energy storage capacity is also very low for the normal PCMs. So to enhance the effectiveness or to enhance the thermal conductivity, there are so many ways we can enhance the thermal conductivity of the PCM by metal fins, metal screens, and other metal structure. But all these techniques, what they increase the weight of the PCM, volume and weight of the PCM within the container. So the new technology, that is the nanotechnology, what we are using. We are preparing the nanofluid. Nanofluid is what? That we are taking the base fluid and we are diffusing the nanoparticles of size 1 nanometer to 100 nanometer. And by a specific process, we are mixing that base fluid and the nanoparticles, and we are creating the nano PCMs. These are the certain thermal stability, heat capability, and the stability of the longer plates. These all are the certain benefits of the nanomaterial embedded PCMs. Here are certain properties that has to be taken considered for the selection process. Like I had already told that melting point, latent heat of fusion, that is the basic chemical and physical stability, that for a specific application where we are using that, so we have to think whether it should be chemical and physical stable or not. Otherwise, it get degraded. And that also we can check with the thermal tester, thermal cycle tester, we can check the stability of the PCM also. Thermal conductivity is one of the major factor, viscosity, and the chemical composition and the physical properties. Just a minute, wait a minute. Sorry for the interruptions. Am I audible?
Yes, sir. Yes, sir.
Yes, sir. Yes, sir. Audible.
Okay. So here are some of the basic works already being carried out to enhance the effectiveness, or basically on the nano energy PCM. These all are the literature review. Basically, paraffin has used. They have used base fluid as the paraffin, and they had diffused different types of nanoparticles to enhance the effectiveness. Yeah. And this is the nano enhanced PCM with other PCMs other than the paraffin, because a lot of work has already been carried out on the paraffin. So we are using different types of PCM for the nano enhanced PCM. Now, this is the basically what is the technique to prepare the nano enhanced PCM. We'll see the practical applications, that how we can use, how we had used this nano enhanced PCM to increase the efficiency or the performance of the solar thermal systems. So to prepare the nano enhanced PCM or the composite PCM, so we had prepared firstly eutectic PCM. Now eutectic PCM is generally word that we can mix two or more than two PCMs. Two or more than two PCMs we can mix to form the eutectic PCM. So we had prepared the binary eutectic PCM. Right? We had taken two different types of PCM, base PCM, palmitic acid and the stearic acid. And we had also taken the SDBS, sodium chlorobenzene sulfonate. This act as a capping agent. And we have taken the nanoparticles, the copper oxide nanoparticles of 50 nanometer size. So please mute. Okay.
Yes, sir. Sorry, sir.
Hello, sir.
Yes, sir, you are.
Hello.
Am
Sir,
I audible?
am I audible, sir? Am I audible?
Hello.
Hello. Yes.
Okay.
Sir.
So this is the firstly we are this is a two-step method to prepare the nano enhanced PCM. In first step, we are preparing the binary eutectic PCM. For that, we have taken the palmitic acid and the stearic acid in a weight ratio. That the specific weight ratio, as already discussed, we can calculate it by using a Schroeder equation. So what we have taken 64 ratio 36%, 64% palmitic acid and 36% stearic acid. We had taken the specific weight ratio. Then we had mixed this both the phase change material, palmitic acid and stearic acid. And what we had done, we had heated and stirring. We had heating this mixture in a beaker with the help of the magnetic plate with magnetic hot plate with magnetic stirrer at a temperature greater than the 54 degrees Celsius. So what we had done, we are just checking that the temperature should not exceed approximately 70 degrees Celsius so that it can properly melted. And at 500 RPM, up to half an hour, we had properly mixed so that uniformly mixed both the PCM. So we got the binary eutectic PCM. Next, to achieve the nano enhanced PCM, what we had added the specific quantity of nanoparticles in the beaker, and for approximately 30 minutes at 500 RPM, we had again mixed the nanoparticles in this eutectic PCM. And after that, we had done the ultrasonication process. This is a major important process because if we will not do the ultrasonication, the nanoparticles will never get uniformly mixed with the base PCMs. It is the mandatory process that we have to do the ultrasonication, and that also depends upon the certain 40 hertz frequency and the residing time. That depends on us that how much quantity of the nanoparticles we are adding, how much base PCM we are taking. So as we had mixed for about 30 minutes, 20 minutes, depending upon applications. So after properly mixing in the ultrasonicator using the probe sonicator, we had crystalline at room temperature that PCM that we had stored for the further so into fine pieces. So this is the basically process two-step method to prepare the nano enhanced PCM. These are the general small. This is a pics that first we had weighted, we weight balance. Then we had taken the two different types of PCM and we had mixed with the help of the magnetic plate with hot plate with magnetic stirrer. And then we had taken this is the ultrasonicator. And when after the ultrasonic process, we had the crystallized the hard part of this PCM into the in the fine grass with the mortar and pestle. Here are the different types of PCM. We got nano enhanced PCM like this is the pure PCM, eutectic PCM. This PCM nano PCM is with 0.3% of the copper oxide nanoparticles. This is with 0.8% of copper oxide nanoparticles. This is 1.5% copper oxide nanoparticles, and this is 3% of copper oxide nanoparticles. Now, after preparing the PCM, there are certain properties we have to check whether it is reliable, it is feasible for the practical application or not. For that, there's a DSC. DSC is a differential scanning calorimeter, but basically it is used to measure the melting temperature and the latent heat of any kind of PCM materials. FTIR is basically used to analyze the functional group, which kind of functional group is available and in what range within the PCM. XRD. XRD is basically used to measure crystalline structure and size of nanoparticles. TG is the most important technique because it reveals the thermostability and the deterioration of the eutectic PCM and a nano-enhanced PCM. Because at what temperature our PCM will get deteriorate. This will analyze by the TGA analysis, thermal conductivity. It's also very important because why we are incorporating the nanoparticles, we are incorporating nanoparticles to enhance the thermal conductivity. So it is a need to measure the thermal conductivity. The thermal cycling test, because as we are preparing the PCM, we are not preparing for a single time, that it will work for a single time. We had kept for any solar thermal system and we are thinking that it will work for a longer duration of time. Means each day it is charging and it is discharging. It gets melted, it gets soluble. Charging and discharging each day, it is working. So we know the reliability, we know the stability, that how much cycles, how much longer life it can work without degradation. For that, we are just checking the chemical and thermal degradation using the thermal cycling test of the PCMs or nano-enhanced PCM. Here are some of the results. Basically, this is a DSC test of the different types of PCM, and this curve shows the latent heat, how much latent heat is absorbed by the PCM. And this is a phase change temperature we are getting with the help of the DSC outcomes of the DSC test. And this is the latent heat. So what you can see that as the concentration of the nanoparticle increases, the latent heat decreases continuously. But the main thing is that we never want to lose the latent heat, because we want the maximum amount of latent heat should be available in our PCM. But here is a drawback of the incorporation of the nanoparticle, that it decreases the latent heat capacity. And why it was? Because during the phase change, the pure PCM is involving in the phase change process, but the nanoparticles is not involved in the phase change process. Therefore, the latent heat of the system decreases. Latent heat of the PCM, nano PCM decreases as well increasing. Okay. So these are the XRD analysis that what we are checking here, that out of the 5 or 6 samples, we are checking that there should not be any shift in the peaks what we are getting. The peaks what we are getting in the base PCM by the incorporation of the nano PCM, the peaks should be same at the same degree that we achieved. FTR analysis also same. We didn't find any new peaks. Now, TG analysis is also that at approximately 200 degrees Celsius, our PCM is very nice working, no problem with the PCM, no thermal degradation. But as the temperature increases, it suddenly drops down this physical and chemical stability. So this is the TG analysis, that this eutectic PCM or palmating study is capable of working up to 150 to 180 degrees Celsius applications basically. Now this is the thermal conductivity basically. That this is the curve that we will more focus, that as we are increasing the concentration of the nanoparticles, the latent heat decreases. As the concentration of the nanoparticle increases, the latent heat value decreases. And so what should be the optimal point? How much we can incorporate, because when we are testing, we need the maximum amount of thermal conductivity and we need the maximum amount of latent heat also. So the crossing point between the thermal conductivity line and the latent heat is the optimal point. Means approximately up to 2 to 2.5% of the nanoparticles we can incorporate. Beyond that, the clustering phenomenon will react. The clustering phenomenon within the PCM, because of the nanoparticles, will act, and it will largely affect the latent heat of fusion, basically. This thermal cycling test also, that's thermal cycle a tester is there, in which continuously we are solidifying, we are melting the PCM, then solidifying, melting the PCM, solidifying. So in a day, 25 tests we can perform. So approx after the 1000 cycle, as 0 cycle and 1000 cycle, we had seen that we not get so much difference. That our PCM is also stable after 1000 cycle also. So this is a thermal cycling test we are using the energy storage materials, basically. This is the application of composite PCM, that whenever this is a solar cell, whenever we have to use the PCM, so either one way, this is a basin liner, that black one, downward surface, the basin we are calling, where we are storing the water to purify. So first one is below the basin liner, we can fill the PCM, or we can fill the PCM in any outer source of container, like we have used the copper tubes and copper cylinders. So we had filled the copper tubes and copper cylinders with the PCMs, and we had see the applications, basically. So these are some of the results, energetic, exertic, economic analysis we had performed. So these are some of the outcomes that we are enhancing the temperature. MDSS1 is the modified solar steel one. That we are getting the higher temperature range because nanoparticle. The productivity also, higher productivity we are getting for the nanoparticles, PCM based solar steel. These all are the certain outcomes. Now this is the design fabric of solar flat plate collector. Basically, this is the flat plate collector for solar water heating up, where we are putting here the phase change materials, basically. Likewise, here you can see the PCM beneath the basin liner we had kept the without PCM and with the eutectic nano PCM, and we had seen the that the energy and exergy analysis we had also performed. Now this is the composite PCM in the eutectic flat plate collector, eutectic water tube collector, basically. And what we had done, we had used this copper tube, copper container with PCM within the solar water heat, within the storage tank of the evacuated tube. Now, this is certainly the different types of solar cooker also. So this is specially designed, consider the solar cooker. The vessel that is used to cook food is specially designed like this. And this is the cooking area. And here we had filled the phase change material. The phase change material we filled is two types of. One is the solar salt. Solar salt has a melting point of approximately 230 degrees Celsius, which includes the magnesium carbonate and the sodium carbonate. And we are also using the magnesium hexachloride for the, in winter seasons, we can use. It has a melting point of 118 degrees Celsius. So as the first the solar radiation strikes towards the bottom area, first this PCM melts, and subsequently it transfers the energy to the inner part. So when the concentrate, when the vessel, the cooking vessel is in the outer atmosphere, so we are getting the cooked food. And as after a certain time, after 3 to 4 hours during the non, we can take out this vessel, and still it can work for around 2 to 3 hours because of the energy stored by this PCM, a huge amount of energy stored by this PCM. So these are the certain applications of the PCMs in the solar thermal application systems. Basically, there are so many applications of the PCM, like in buildings also. Smart textiles we are using, gloves we are using in the industry to store the excess amount of heating or the cooling effects. Biomedicals, cooling systems. Electronics we are using PCM to store the heat that is generated within the system. And automobile industries. These all are certain applications. These all are the references. Thank you. Any questions, please?
So, good evening, Dr. Rahul.
Yes, sir. Good evening.
It's very excellent presentation on PCM. And my question is that actually, is there any threshold melting temperature for higher efficiency of the PCM?
So basically, threshold melting point, what actually, there are so many types of PCM available in the market. And for the specific applications, actually the first, the major challenge is the selection of the PCM. when we have to when we have to select the PCM, we have to look our comfort that for what application. For example, a certain application that when we are using the solar stills, the maximum temperature we are getting, the basin temperature of the water temperature, we're getting around 60 degrees Celsius. So if we will use the PCM of 40 degrees Celsius, then it will not store a huge amount of latent heat. It will mainly depends upon the sensible heat. And if we will take the PCM of 90 degrees Celsius melting point, and it will not melt. So there is no threshold limit for the PCM, but the selection of the PCM that for around that 60-degree temperature we are getting for our application. So we had chosen this eutectic PCM of 54 degrees Celsius. That after 54 degrees Celsius, our PCM is completely melted and it stores both the sensible and the latent heat.
Understood. It is actually application based, actually.
Yeah, definitely, sir. Application. And lots of PCMs are available in the market.
Any other questions from participant side?
हेलो
Yes, sir, please.
हेलो
Yes, sir, please.
सर ये जो भी सर आप पढ़ा रहे हैं सर इसका पीडीएफ प्रोवाइड हो जाएगा क्या सर?
We'll try.
सर
Actually,
ग्रुप के थ्रू जो हम लोग हैं ग्रुप के थ्रू तो पीडीएफ हो जाता तो सर सही रहता सर.
Actually, from my PDF, my PPT, then I can share you. But regarding the other experts, we have to take the permission that we.
जी सर.
We'll try to provide you.
ओके सर, थैंक यू सर.
Hello.
Yes, Dr. Sanjay. Your order.
Yes. My question is related to the use of PCM in there is a solar chimney power plants, and
Yes, sir.
in that case, the large number of halistutes are used for that power plants, and will be stored in different chambers and use it. So for this large scale applications, whether these PCMs are useful, and what is the scenario in world regarding this?
Sir, what should be a temperature approximately there in solar chimney?
It is up to 700 degrees Celsius.
7. Because, sir,
what happens that
yes, sir.
energy is to be stored in the different chambers. One is cool chamber and second one is melting chambers. So in that case, whether it is applicable?
So basically, regarding the solar chimney, I had not gone for the practical of the solar chimney, so I can't say so much. But regarding the solar concentrated solar power plants, that also works on a very high temperature. And regarding the waste heat recovery systems, that is also working on a high. So we are having an application of the PCM. But for regarding the solar chimney, because I had not taken the physically, I had not seen or not gone through this concept of the solar chimney. So it's quite tough for me to say that which type of PCM or how much the reliable the PCM will be there.
Okay. Thank you.
Okay.
Any other questions? Any other questions from participant sides? Now it's time to take thanks our speaker. On behalf of the Department of Mechanical Engineering, it is my privilege to deliver the vote of thanks to our vote of thanks for this enriching session on energy storage technology by Dr. Rahul Agrawal. Dr. Agrawal, your profound knowledge and insight into energy storage system and their applications have been truly enlightening. Your discussion on advanced materials, innovative experiments, and practical solution for renewable energy integration has provided us with the valuable perspectives. The examples of your work, including modification in solar steels and the development of smart solar cookers, have been truly inspiring and reflect the depth of your research and commitment to sustainability. We sincerely thank you for sharing your expertise and for addressing the challenges and opportunities in energy storage technologies so comprehensively. Once again, thank you, Dr. Agarwal, for
No
your
problem.
time and valuable contributions to this program. We look forward to more opportunities to learn from your expertise in the future.
Thank you
Thank you,
so
Rahul.
much. Thank you so much, Rohit sir.
Our next session will start in 10 minutes.